So, how deep is the longitude? The common consensus seems to be that, well, it's pretty okay for a default aircraft. But the Longitude is actually an extremely highly advanced automated aircraft that keeps the pilot's workload very low. And as a result, you don't always see what goes on behind the scenes when you're flying the plane. But today we're going to go through each system and see just how deep the Longitude is. So here we are with the C700 Longitude at DuPage Airport. That's DPA. Shout out to the Flight Effects folks for their incredible rendition of this airport. You can see here the super unique FBO. Just a very cool building. And it happens to be my home airport, so that's why we're here. The very first thing we're going to take a look at today is the hydraulic systems of the Longitude. So here we go. Let's dive into the hydraulic systems. All right, so here we are with the hydraulics controls. You'll see we've got the pump switches for pump A and pump B, and we've got the PTCU knob. That's the power transfer control unit, and we'll talk about that a little bit later. But these are the primary controls right here, as well as the rudder standby. These are the things that are connected to and or control the hydraulic system. And you'll notice we also have the hydraulic synoptic up, which is displayed on the MFD. Now we have it popped out so we can look at this and not have to change the camera view a whole bunch of times. So what is displayed all in this view? Well, you've got two independent hydraulic systems. There's a system A and a system B, and we've got some information here about both. So this is the current pressure of the system, this is the current temperature of the system, and this is the amount of fluid remaining in the hydraulic reservoir. Anything with green is hydraulically connected. So the reservoir is green, it has fluid in it. And you'll see down here we've got the spoilers are also in green, and we have the brakes are in green as well. Now we also have these very strange pill-looking things with arrows, and those are actually the hydraulic accumulators. They store hydraulic fluid. They're sort of a one-way valve. So they bring fluid in, and then when hydraulic power is required, they can expel that fluid in order to power things. So these are sort of you can think of them as a hydraulic capacitor, like an electrical system has a capacitor, or a small battery. One thing you might be thinking to yourself is, well, if the hydraulic system is off, I see these switches, they're not powered, how is it that there is some hydraulic fluid missing from the reservoir, and how do these hydraulic accumulators have any fluid in them? Well, what we did is we chose to model the normal configuration you would find the aircraft in. After the aircraft is powered down, these hydraulic accumulators take a long time to self-discharge. They're designed not to do that. So they have very, very, very low leakage. So if you're using the aircraft with any frequency, you will not ever see these not have anything in it. But what we can do is I can show you what happens when the plane is normally powered up, and we can see how these become charged. Okay, we've switched our view a little bit here. We have our hydraulic controls up in this corner, and we have our parking brake down in this corner. And we're going to be showing how the hydraulic accumulators work and how they become charged when you first start up the aircraft. So something super interesting to note is we actually are using real hydraulic fluid simulation in order to power this. Including the correct fluid flows and the correct capacities from the real parts that are in the Longitude for these hydraulic accumulators. So what you're seeing here is an actual simulation of the fluid moving in and out of the accumulators, in and out of each system and line, and you'll see where the fluid goes, and we'll see it get charged here. In order to get some fluid out of these hydraulic accumulators, we need to actuate some things that are using the hydraulic accumulators. So in this case, the parking brake is held in place by pressure from the hydraulic accumulators. The entire system acts as sort of a one-way valve with the brake pads pushing against the calipers. So when the parking brake is on, there is no fluid leaving these, and you get a constant 3,000 PSI pressure of the brakes from the hydraulic accumulator fluid. But what we can do is we can turn the brakes on and off a couple times and get some of that fluid to be pushed out of the brakes back into the hydraulic system. So we're just going to do that a few times here. So we'll turn it off, and you can see the brake pressure go down, comes back up, and some hydraulic fluid got pushed out of the accumulators, and now the total brake pressure actually is a little bit lower. And you would note that these values here in the reservoirs, we've got a little bit more fluid that got pushed back into the reservoirs. So we'll just do this a couple more times. And let's get it down to, yeah, 2,700. That seems like a good stopping spot. So the brakes are a little bit less pressure. We've got more fluid that got pumped back into the reservoirs, and we're ready to show exactly what happens when this whole system is powered on normally. All right, so back at the this view, which gives us a little bit better picture of our hydraulic system controls. Now is the time where I explain exactly what the PTCU, the Power Transfer Control Unit, is. So the Power Transfer Control Unit starts its magic here with the M/G. You see that on the circle. That stands for motor generator. Now the PTCU can work in two directions. The motor can power via electrical power, can power these pumps, which brings hydraulic power to System A or System B, or this can actually be operated in reverse, where the pumps from the engine-driven hydraulic side can go back into this system and power the generator, in which case electrical power is generated. So you can use electrical power to generate hydraulic power, or you can use hydraulic power to generate electrical power. It's a really unique backup system that the Longitude has, and we simulate it extremely faithfully. We have all the modes simulated, we have all of the correct delays between the mode switches simulated, all of the automation, which the computer handles in the PTCU. All that stuff is automated and super cool. So why am I telling you all of this about the PTCU now? Well, normally, this switch, when you get in the plane, would be in norm. And these positions all have different meanings. So I'll go through these a little bit briefly. So the aux A position means that we want the motor of the PTCU to power the System A side hydraulics. So it would go from here and flow through the system. If we go to aux B, which is a little bit obscured, it means the same thing. We want the motor to power the B side hydraulic system. And then if we switch it over to Hyd Gen, that means we want the hydraulics to power the generator, which means we want it to generate electricity instead of hydraulics power. Norm mode, this one in the middle here, is the fully automated mode and the one that the plane is normally set to. And in norm mode, the PTCU controller has its own set of logic, its own set of fallbacks, and it controls the operation of the PTCU in total. And that includes transferring fluid between the sides. It controls engaging aux A and aux B. All those things, it does those automatically, so the pilot doesn't necessarily have to do those things. And one of the first things that norm mode does when the plane is powered on and the parking brake is set is it makes sure that the parking brake accumulators are fully full so that the parking brake can be engaged. So we're going to set it to norm, and we're going to watch the system do that. We're briefly going to have to take it through aux A, so you see aux A light up briefly. But normally what it does is it engages System B and then System A. So we'll switch that over here. And you see aux A light up briefly, and now we're in the norm logic. So System B is being powered in order to fill the accumulators, and then we'll see System A being powered in order to fill the accumulator on the System A side. And once that cycle is complete, then we've got full pressure in the hydraulic accumulators for the parking brakes. You'll notice a lot happened here in those few seconds during the power on cycle for the parking brakes. You'll notice that the hydraulic reservoir, the fluid level got lower, and that's because the fluid was pumped into the hydraulic accumulators, and that happened on both sides. And you may have noticed that the pressure of the system, it went up, and then the temperature of the system went up because of the heat generated by the hydraulics pumps. So all of that is happening when you engage the pumps. The other thing that you'll see is this temperature is actually dropping, and that is because the hydraulic system is actually cooled by the fuel system. And the fuel right now is relatively cool. It's probably around air temperature. So you'll see that in the fluid, the fuel is a very large surface, and it can very quickly dissipate. So you see this temperature is coming down relatively quickly. And a couple other cool things to note about the simulation. So Again, these are all the real quantities of fluid in these systems, and we are using real hydraulic formula in order to push fluid into and out of these systems, as well as real temperature formula in order to model the heat sinking of the fuel, as well as the heat that goes into the system from the friction generated by the pumps. Some other interesting norm mode automation is the priming of the hydraulic system. So the PTCU, when in norm, the motor will prime a system when an engine is about to start so that the engine-driven hydraulic pump is not starting dry. It primes this whole thing. So if we switch this to run, we'll see the PTCU kick in because it knows that we're about to start this. And you can see that the motor generator now is automatically switching to aux B. So it's powering the B side. And you can see the arrows are pointing towards the hydraulic pump, which means that it's the motor and not the generator side. If it was the generator side, this would go in the other direction. So this is now priming this system for engine start. And when the engine is started, then this pump already is operating within some hydraulic fluid and is not dry. Back at our view of the hydraulics system controls, let's take a look at the hydraulics pump switches. So we have two switches here, pump A, which operates system A logically, and pump B, which operates system B. And they have three positions, shut off, min, and norm. Shut off is where the pumps are entirely cut off from the engine and they're not running, even if the engine is running. Min is a minimum pressure setting. It only goes up to 1200 psi. It can be useful for some emergency situations. And norm is the normal setting. It's full pressure. So let's turn on system A here, and we'll flip it to min. We can see that get to 1200 psi. Our temperature is going up as a result of the pump, and we can just switch it into norm. And we'll do the same for pump B. Perfect. And now, as you can see, a couple other things lit up that are not connected to any hydraulic accumulators. That is our rudder systems. It's our thrust reversers, and it is nose wheel steering and our landing gear system. So those are the things that, some of the things that require hydraulic power. So those things are now working, and the entire plane has hydraulic power. And finally, the thing that we haven't touched on yet is the Hyd Gen Mode and how that works. So to demonstrate that, I'm actually going to cut our generators. So let's turn all of our generators off here. And we should see some battery draw show up and some warnings. Let's clear those. We know what we're doing, or at least we think we do. So all of our generators are off. And you can see that we've got a fairly significant drain on the batteries here. But if we want to rectify that, we can actually switch our PTCU into Hyd Gen Mode, and we will start to get power from the PTCU itself. So now the system B is powering the motor generator on the generator side. It's being used as a generator. And that is basically a generator that is giving electrical power to our electrical system. And you can see here, we are now charging the battery at a small 1 amp. We didn't use it for very long on its own. And of course, we get a couple warnings about doing that. Which we are free to ignore if we know that we needed to do it, but it's telling you that there's a situation that's not sort of the normal situation here. But yeah, so that's the motor generator, and that's how we get power back into our system if all we have left is hydraulic power. And finally, the last thing we haven't talked about here is this rudder standby button. Rudder standby is actually a self-contained hydraulic system for the rudder only. Normally the rudder is powered by the hydraulics of the plane, but if those systems have failed, you've got a rudder standby system that is an enclosed system that will give you rudder control. So we have it set off. If we turn it on, then it's in the norm mode. Normally the rudder standby would not be activated unless you lose hydraulic power, which we can actually simulate. So if we set these to shut off, you'll see these systems go into a lower mode here. And now the rudder standby has actuated. So how does this all work once we're in the air? Well, I've got us cruising here now at 32,000 feet, and as you can see, we've got a new line here, this white dashed line. That's actually the transfer mode of the PTCU, and what it does is it ensures that there is equal pressure between the two sides. Right now, it's the same between both sides, so we just have this this little dash. But if I induce a failure or simulate a failure, and we say, actually, we lost the System B pump. Well, now we've got transfer from System A to System B, and the PTC automatically handles that transition. So we haven't lost any functionality yet. But the question becomes now, what happens if we lost both pumps? And so if I turn that off, the best it can do is it goes into this transfer mode. Now, the problem with that is there's no pressure on either side, and it doesn't automatically go into a mode which gives you pressure. So in order to induce that, we'd have to go to aux A, which now powers that side, or we would have to go to aux B, which powers that side. We can't do both now. In this particular situation, we can only power one side or the other. Now, if I go back to norm here, let's take a look at what this has done for our control authority. We're cruising here at 32,000 feet at Mach 770, and we are simulating a complete hydraulic failure of both pumps. And we are going to see exactly what that does for our control authority. So I'm going to take it off of autopilot and just do a little wiggle waggle here of the stick, and you'll see just how sluggish it is. Take autopilot off, and I'm just going to do some full deflections of the stick. And the Longitude's pretty nimble. It's got a pretty strong bank rate, but we'll see that it's not going to be very fast here. So that's full deflection. Get it over to the other side. Not very fast. Get it over to the other side. Yeah, not particularly fast. And the reason for that is because we don't have our roll spoilers right now. All we have is our ailerons. The ailerons are a direct mechanical linkage, but the roll spoilers give us a lot more authority than we have with just the ailerons alone. Now you might go, why do we not have roll spoilers even though these are green? Well, these hydraulic systems are only powered in an emergency for ground spoilers. These will only discharge when you use the ground spoilers, and that is to give you sufficient braking on the ground. And if you have a hydraulic system failure, you will still be able to engage the ground spoilers on the ground and get sufficient braking. That's more important than having them, the roll spoilers available in the air. Now, one thing we can also show here, though, is the rudder is using the rudder standby system because the rudder standby system is set here to norm. So if we attempt this same test, we've got the autopilot off, we've got hydraulic system failure simulated. We can try our rudder, and we get pretty good rudder authority. I'm not going to go all the way because this is one big rudder, and that could certainly be not very great at this altitude. But yeah, you notice we're going left and right quite easily. However, let's say for some reason we also lost the rudder standby system. There's a full system leak. Maybe there's a puncture, some kind of physical damage. So we can simulate a rudder standby system failure as well. And that's going to kick off our yaw damper. It's going to make our rudder fail entirely. And let's see exactly what we get now as far as control authority goes. None. This rudder does not move at all. So that makes it very difficult and is the reason why the rudder standby system exists in the first place. So what we can do now, however, because we have the PTCU, we have electrical power, and we can get ourselves out of this situation. We can move the PTCU, let's say, to aux B. Now we've got rudder power. Now we've got some spoiler power. So we should have roll spoilers and we should have rudder. So if I do a little rudder test, indeed we've got rudder. Rudder is back. If I do a little roll test, indeed it's nice and snappy. So you can see all these things are simulated. We are pushing fluid to all the systems. We are simulating the control authority differences when the systems are not working. So you are able to practice all the abnormal procedures you would have from actual individual systems failures by just turning some things off and on and seeing what happens with the systems. So this is kind of a very complete simulation of what the Longitude has in real life. We're not really missing anything here. This is really what it's all got. So it's incredibly deep, and that pretty much rounds out what we're going to see out of the hydraulic system. So next, I think we're going to go to the electrical system. We are back here down on the ground at beautiful DuPage Airport with the lovely FBO in front of us. And we're going to take a look at the electrical system. So the very first thing we're going to take a look at is the automatic bus tie logic. And the bus tie logic is automatic on the ground always. It is not pilot selectable, but it is interesting how it works. So we're going to take a look at that. And the very first thing that I'm going to do is I'm going to turn on one of these batteries. And we're just going to start with the left battery. So let's switch that on. And we'll wait for the systems to come up, and then we will select the electrical synoptic. All right. Screen is on, aircraft systems, synoptics, electrical. So now we have a full diagram of exactly what is connected to the electrical system. We've got our batteries at the bottom, we've got our emergency bus, we've got our mission bus, main bus, and int bus. There's actually 2 int buses per side. And each of those is connected by various breakers, which you can see actuated on here. And anything that is green is something that presently has power. Now, you might be wondering what exactly happened here. So you'll notice that this bus tie is closed, but we didn't close it. It automatically closed. When the system detects on startup that there is only one side with power, it will automatically engage this bus tie so all the systems can be powered. And as you'll note here, we've got a pretty severe draw as a result of that. And you'll also note that our battery temperature has gone up as a result of that draw. Now we've got a very complex battery temperature simulation, which uses the draw to figure out exactly how much heat is being generated by a particular electrical draw. So lower draws will generate less heat, higher draws and higher charges will generate more heat. So that system is all simulated. Now what we're going to do here is we're going to turn on the other battery and we'll watch how the bus tie changes. So once we have 2 independent power sources per side, or 1 per side rather, you'll see the battery comes on. After the bus tie senses the voltage, the bus tie is released, and now we have an open bus. So these sides are now operating independently, and you can see that each battery is drawing less power because it's only operating half of the components. It's not the exact same draw because they're not the exact same components, but you know, it's somewhat similar. So now the systems are isolated from each other. And that's part of what the automatic bus tie system is meant to do, is make sure that the systems are isolated when they should be and tied together also when they should be. And the next thing that we'll do is we'll start up the APU generator and see how that changes things. Over here at the APU, we're going to get the APU started and see what that does to the electrical system. So let's start the APU process. So the first thing we're going to do is we're going to switch the APU to on, and then take a look at the APU fire light. That should go on and then go off, and it does. What's happening there is when you switch the APU to on, the thing that it does is it runs the APU fire system detection test. And so that runs the light on and the light will turn off, and that tells you that the test was successfully passed, and now you can turn on the APU. So let's do that. We're going to start the APU and we will watch the EGT rise. One thing to note about the APU on the Longitude, it is fully automatic. If you were to get a hot APU start or any other APU start failure, it would automatically kick off the APU start process and shut down. So it is a fully unattended APU. There are some limitations, and I think they're outlined in the operator's manual, but it's intended for you to be able to use it and then be able to walk away from it. One thing you'll notice now is, wait a minute, the bus tie is closed. Why has that happened? We didn't close it. Well, it's still part of this automatic system, and what the system has detected is we've actually got an active power source, not just a battery, on only one side. Therefore, we need to tie the bus in order to have that source charge the batteries themselves. So the system understands that if you've only got one on-side power source, you're going to need to tie the bus together because you want the batteries to be able to be charged, and you want both batteries to be able to be charged from the active power source. In this case, I was running this left battery more than the right battery a little bit earlier, and we've got a lot more charge going into this. So you actually notice we've got a battery low takeoff indication, and that's just telling you that the battery requires a lot of charge, and that's why we've got a whole 20 amps going in here. That's going to come down straight from the APU. And actually, this is great, and that message just went away. So it's charged enough now. It doesn't take that long to bring it back up. Unless you have it really, really discharged. But the system wants it to be particularly charged. So that's why that message comes up. But right now, bus tie again is closed because we just have the one on-side active power source. We can actually do something interesting here and break this bus tie by putting in another active power source on the right side. And we actually happen to have external power available. So if we connect that, you'll see we've got active power sources on both sides, and we no longer need the systems to be tied because each side can individually power the batteries and charge the batteries. So the bus tie will go open in that case, and we can take that back away by just setting the external power off. The bus tie will detect that state, notice that there's only one on-side power source again, and we'll get back to the tied bus state. We've gotten some questions about the position of the generator switches in the normal cold and dark state, and why are they on? Normally in most planes, you'd have the generator switches off, and then when the engines are on or when the APU is on, you'd move those switches to on so as not to cause the generator to experience a lot of load because it's connected to the electrical system early before the windings are spinning fast enough before the whole thing, the generator is giving enough power. And that can cause a generator failure. However, on is more of a norm mode. What you'll notice here is you'll see that that this is connected, but you'll see that even though I have these switches to on, the right and left generator switches, I'm just going to zoom in here so we can see those a little bit better. Even though those are selected to on, these are actually disconnected from the bus. And that is because there's an automated system that connects these to the bus only when the load has, or the voltage and the generator RPM has stabilized. And if it has not yet, then they will not be connected to the bus. So for the APU generator, we can actually take it offline here. And you can see that it will be disconnected from the bus. We'll see that our bus tie will go to open again because we're back to the dual independent battery power source configuration. And I can flip that back to on. The APU generator is reconnected after a slight delay, and then everything will go back to being bus tie closed so that the APU can power both sides actively. The next thing we're going to do here is we're going to get some engines going, and I'm going to skip the whole engine start process, but we'll fast forward to where the engines are already going and the generators are already going. Okay, I lied a little bit. I actually forgot. I do want to show when the engine comes online, the generator stabilizes, and then that's when the bus is automatically connected, when the switch is set to on. So the engine is coming online, and there you go. The bus switch automatically connects. No broken generators. Okay, now we're actually back with the both generators on state. As you can see, now we're bus tie open. Why is that? Well, we've got two on-side systems, two on-side power sources operating, just like we did when we had the APU gen and external power both connected at the same time. So now the systems are fully independent. You are able to charge the batteries from both sides. So the system says, hey, I can remove this tie. We don't need that anymore. And so the system is now stable. However, we can change that. For example, if we turn this generator off on the right side and make it so that still just the left side has an on-side power source, you'll see the bus tie is now required. So the entire bus tie action has a lot of automation behind it that makes sure that you don't really need to worry about it as a pilot. It's just another thing that, that reduces the pilot workload and makes it so that there aren't so many failures possible and reduces the maintenance cost, honestly. So if we switch this back on, there you go. Now the bus tie is going to be open, And we've got independent systems again. One question we see asked a lot is, what the heck is no standby data? And also, similarly, people go, well, the standby power on, is that some kind of emergency battery system? What is that? Well, actually, this is just power for the standby instrument. It has nothing really to do with powering any standby systems. It's really just for the standby instrument. And the no standby informational message here is just telling you that this system is not receiving any data from the standby instrument. So the way to fix that, we just turn standby power on, and the standby instrument goes on, and now the message is off, and we have standby instrument doing what it needs to do. There's some more stuff about the standby system though, and I'll show that in just a second. So the standby instrument is actually powered by its own battery that is isolated from the rest of the systems, and it receives charge from the left emergency bus. And it's not indicated anywhere on this electrical synoptic, and there's only one way to tell if it has enough juice. And the way to tell that is by holding down the test position. If this light is green, then your standby battery, which is again just for the standby instrument, has enough juice. And you want to check that before you leave, because you want to make sure that if you have some sort of failure, that you'll be able to have at least a standby instrument available. And finally here, I've put the plane into kind of a weird state with no power. I've got the engines on still. But you notice that the standby power switch now has a red light. And what that indicates is the standby battery, which powers the standby instrument, is now discharging. And so that's just a reminder, especially in case you power the plane off and you forget, that the standby battery is in a discharge state. It's not being charged by anything. Now, if I return power to the plane, that light goes away, and the standby battery is now again being charged by the left emergency bus. And so that's basically it for the standby instrument power system. So some other cool simulation notes here about the electrical system. This is a custom electrical system, as you can see. In particular, we've got a custom battery modeling, which has internal resistance and voltage drops, and as a result has the correct charge and draw amps. So you don't see things like infinite charge when you charge the battery. So we've got this drawing just a little bit, just been a few seconds here. And when I turn the generators back on, you're going to see that we get just a little bit of charge amps. And that's because the batteries were only a tiny bit discharged just for about 30 seconds there. So the electrical system is very customized and very deep. We also have all of the right stuff connected to the right buses. And just going over the buses a little bit, the emergency bus powers everything that's strictly needed, just bare necessities needed to land the plane in an emergency. The mission bus is sort of one step up. It's got everything you need to fly normal operations, but without redundancies. And then the main bus gives you the redundancies back. And the int buses are just for the cabin and interior systems, which are not modeled as there's no interior, unfortunately, in the Longitude. So that part is left out. But the rest power the things that you expect. So, we can turn off our connection from the emergency buses. And this is an interesting detail here. The system is telling us, hey, look, we've got a problem. You've disconnected the buses, and that's not good. We still have power because the generators connect to the mission buses, but this is disconnected. However, if we were to lose generators, now we've got some failures. We can strictly still land the plane, but we've got some issues. So you see that we've got the stuff connected where it needs to be connected. And you can manipulate the system to generate a number of emergency situations and abnormal ops for you to play with. And we'll actually try something like that in the air here. All right, so we've slewed ourselves up to some, 22,000 some odd feet here, and just holding here with autopilot so we can check out a few things. And what we're going to do first is we are going to pretend we've got sort of an engine out situation. So let's turn off our left engine, and we can see that we've got engine shutdown. It flashed a firewall for hydraulics for a second. Now we've intentionally shut down this engine, so it only flashed that for a second. Now it's telling us, hey, you shut it down on purpose. If it was an actual failure, it would show a different warning here, but we're just going to roll with this for now. So let's say we've got an engine that's dead, and you'll notice that over here, it's been disconnected from the bus. It's starting to spin down slow enough that we're losing voltage. This generator is not usable for us, obviously. The engine is not running. But let's say we got ourselves into even worse trouble here, and suddenly we are not operating with the right generator. So let's say we've got a right generator failure. We can practice that also. We've got left engine out, right generator failure. Here we go. Now we're disconnected from the bus. It's going to yell at us because it's telling us, hey, you turned it off. Going, yep, we understand. That's fine. We're practicing. Now you notice we got a pretty big draw on these batteries. These batteries are not going to last a super long time in this situation. But we have an engine that is on. What does that mean for us? Well, that means that we have hydraulic generator power that we can use. And in order to do that, we can go over to our system over here, our PTCU, and we can switch that to Hyd Gen. And there you go. You see suddenly we've got power here from the hydraulic generator. And you see this is going straight into this battery here. So Hyd Gen on, it's telling us that that's on. We still have our generator off. We understand that. And here's where the bus tie situation changes. And the load is very high in this generator. We're probably going to want to shed. 100% is not where you want to stay. And the generator is only rated for a certain amount of load. And what we're going to do is we are going to turn off the mains. And we are just going to do the mission buses. Now we still have a lot of load. That's okay. With the mains off, we've got enough power in the hydraulic generator in order to do what we need to do in order to fly the plane. We could take away the mission buses too, but that would be a little bit more difficult, and the hydraulic generator is able to power these. So this is fine where we're at right now. Now what I was going to say before we got our warning about the hydraulic generator load is that the bus tie did not automatically close. We still have a huge draw over here, which is not what we want. So how do we fix this situation? Well, bus tie is no longer automatic once you leave the ground, once you don't have weight on wheels anymore. Now it's at pilot's discretion. So this button actually does something. So we can tie this ourselves and make sure that the hydraulic generator is also charging this battery and is also powering this bus. Which is exactly what we want. So now we've got everything tied together, and we have successfully avoided or mitigated this particular failure situation, and we can continue on with our flight, probably abbreviated at this point. And finally, one little last bit of automatic bus tie logic for when you shut down the plane is the automatic bus tie, when you first turn on the battery, does not apply when you start to turn off one battery. So if you're shutting the plane down, and I shut down one battery, you can't see it on this screen, but you can see here the bus tie remains open. And then you can reset everything by turning the battery to off. And when you bring the system back up, you get the normal system on bus tie. So if I just have one battery, now our bus tie is closed and we're powering everything so that everything can come on. Hit the other battery, the bus tie will open. Again, turn one battery off. The bus tie will stay open because it assumes we're powering down the system. And other battery off, and we're off. And I think that basically takes care of the electrical system. Now we get into one of the most complex simulations in the Longitude, and that is the pneumatic system, or bleed air system, which ties into a number of other related systems, including the environmental control system, as well as the pressurization system and the anti-ice system. So we're going to kind of tackle those a little bit as a group, but just note that the whole pneumatic system is also a custom simulation. So there is a lot going on under the hood. You see a lot of these valves here. There are even more valves and lines. We're using a network flow system that traces, the flow of air from all the lines and valves. And there's more underneath the hood in the real plane that we're simulating that you don't even see here. So we're going to start by starting the APU, and we'll see where that gets us. So we're just going to start the APU here. We're going to skip checking the fire test. We'll just get the APU going. And we see the EGT is going up. EGT looks good. RPM looks good. And that's going to take a little bit to stabilize. Climbing. And okay, we've reached full RPM. So you notice that we don't have bleed air yet, even though it looks like we should. This is in norm, and norm would normally have that open. However, it takes some time after the bleed air system, or after the APU is stabilized, in order for the bleed air system to open up. And that's for a number of safety reasons. And in the Longitude, it takes 30 to 60 seconds, and then the system will open up and you'll see bleed air flow into the rest of this diagram here, though. But right now, yes, it's not there yet, but it will be. And there, just switched. And we've got flow. Valve opened, and there's actually two valves here. There's the main APU bleed valve, and then there's the valve actually at the APU itself. That's why the little bit of delay here. And now, if you'll notice, it's pretty quiet, but you can hear the air coming from the environmental system. So we have that going now as well. Now you notice the line that we have tracing from the APU here goes to heat exchange, ACM, and then finally into the cabin and the cockpit. And you notice that our supply temperature is climbing, and that's because we're getting hot air from the APU, and it's going through the heat exchanger and ACM, which is air cycle machine. It's an air conditioning machine, and that is conditioning the air to bring it to the correct supply temperature in order to modulate the temperature in the cabin, which you'll see is now matching our selected temperature of 21 Celsius. And it doesn't take very long to get some air in here. So this is a much more comfortable temperature. It was a little bit chilly before, not too chilly. But now we're at the normal default temperature, which is selected using these two knobs here. The APU bleed button only has really one mode. That's the norm mode. You can the norm mode opens this up when the APU is powered and closes back when it's not. That's all it really does, but you can turn it off manually in case you had some sort of leak in this line area. And that will cut off the flow of bleed air from the APU. And you'll notice again, it's quiet. We don't hear any more whooshing. We have no airflow into the environmental system, so all that stuff is shut off. So if we turn it back on, we'll see that this lights up green again, and we'll hear the air from our air vents in the cockpit. And we'll start getting supply air again. One thing that you don't see indicated here is actually the bleed air from the APU into the left and right engine air starter system. But you do see it indicated up here. We've got 32 PSI from APU bleed air into each starter, and as such, we can actually start one of the engines. So what we're going to do is we're going to start the right engine. We'll start that right now, and we'll switch this to run. Hit the start button. And that is the proper procedure in the Longitude. You go to run first and then hit start. The start is completely automated. There's no need to hit the starter and then go to run. That's not the procedure. And you notice that we lost bleed air to the air supply, to our environmental system. That's because this automatically shuts down from the APU source and routes directly to the air starter system of the engine that got the start request. And so you'll see that kick off, and you'll actually hear that kick off. You hear the air come off. You're not going to hear it anymore when you start the engine. But now our engine is started, and we've got bleed air both from the APU, and we also have bleed air from the right engine. Looking now at the right side bleed air controls, we've got right engine bleed air, which right now is set to norm, and the right pressure source, which is also set to norm. And the difference between these two is the right engine bleed air is before the cross flow valve or the bleed isolate valve, and the right pressure source is post the cross flow valve. So if we turned off right engine bleed air, you can see that we lose this as a source. This is no longer green. We turn it back on, it becomes green. Similarly, for right pressure source, if we turn that off, this is no longer green. And if we turn this on, it becomes green. So in this case, what we can do is if we wanted to go to the left side, we could use this bleed isolate switch, which allows us to go to cross flow. So now this engine is also feeding the left side pressure source. So if for some reason we needed to cut off the right side pressure source and leave it feeding the left side, maybe there's some kind of leak in this area, we could do that. And now we've got that area isolated. We can return back to the normal configuration and turn the bleed isolate back to norm. So we've seen the right side controls, and now let's take a look at the left, and we're just going to start up the left engine. So same process, go to run, hit the start button, N2 comes up, fuel gets introduced. And one thing you'll notice is we still hear the air system churning. We still hear our vents in the cockpit. And that is because when you have the right engine on, the right engine is able to supply the supply air for environmental controls. And the APU is able to supply the air start for the left engine. So you don't lose the air conditioning while you're starting the left engine. And that's why it's preferable to start the right engine first and then the left engine. But let's check out a couple different other configurations of start that we might have. Here we have this different configuration where the left engine is running and we want to start the right engine. And so let's try and do that. Now you'll notice as soon as we hit run, because it's expecting to start the engine, suddenly we lost all of our air and we have no more green lines. Now, what is the technical reason for that? Well, it turns out that the APU is actually only connected to the left side bleed air manifold. Now, you don't see the air start lines or valves in here, but this diagram sort of indicates that. So you see it's only on the left side. As such, in order to power the air start system, it has to go to the left side in order to go to the right side. So in order to get to the right side, we need to cut off the left side entirely so that the bleed air doesn't go to both sides at the same time and thus be unable to start the right side engine. So we can just now start the right side engine. Ignition coming up, N2, ignition. We've got fuel, ITT. And it should settle in very quickly. And now we have all of our air systems. So we've got everything running. APU, left pressure source, and right pressure source. All right, but what I hear you ask about opposite air starts. So if for some reason we had an engine going, but we couldn't use the APU to start the left engine, we can start the left engine using bleed air from the right engine. And so right now we've got the APU off, and then we can start the left engine. And that looks like this. N2 coming up. Fuel's in. ITT coming up, N1 coming up. Let's make sure we have our cover closed. And there we go. Now we're stabilized, and now we got air from both pressure sources. So once we're in this state with everything going, now what we can do is we can route this stuff in all kinds of interesting ways, which is what makes this system so complex. For example, if we were to turn off the right pressure source, and then also say, well, we don't have left engine bleed air anymore, Now we have no air, but if we open up our bleed isolate, we can take our left pressure source from the right engine bleed. And so this goes all the way across the manifold to the other side. So that's one way we can deal with that particular problem. Similarly, we can actually isolate individual pieces of the environmental control system. So we have it in norm, which means that we have the heat exchanger and ACM running, but we can have just the ACM running, which only takes from the left side pressure source, which means that if we don't have a left side pressure source, we're sort of forced to do the bleed isolate crossflow. So that might be one reason you have to go in that direction. Maybe you have your left engine is out and you've got some sort of heat exchanger failure. So you would switch for that reason. Similarly, if we go back to our initial configuration, just go back to norm. Now we have everything reset up. We can actually go to heat exchanger only. Now that's a little bit more interesting because that can be fed from either side. So there's a lot of different ways that this can be manipulated. And it's all tied into this internal network flow system that supplies all this simulated air to all the different valves and lines and all that kind of stuff. And there are other ramifications of having the ECS system in these modes that we'll get into with the pressurization system a little bit later. But as far as the bleed air system goes, this is sort of the long and the short of it. It's fairly complicated, but once you get into this state, it's not something that you really have to manage unless you were dealing with a leak in a particular line or something like that. So given that, I think probably the thing we'll do now is actually take a look at the pressurization system. Here we have the pressurization controls, and they are relatively straightforward. There's not a lot to this. So there's only two modes to the pressurization controller. Normal, which means that the computer is controlling the pressurization, or manual, which means that you are. And in manual mode, you'll able to change the cabin altitude by pressing the switch. There's down, and you can see the cabin altitude change here. There's up, see it change back. And that's all you really need to do with that. It's fairly straightforward. But normally you'll be flying along in norm mode. And let's go to the GTC and see how the pressurization system is set up. Here at the GTC, if we go to aircraft systems and leave it on controls, go to cabin pressure. And here's the pressurization system controls. For the automatic controller. Not very complicated controls here. We've got a normal mode, we've got an altitude select mode. In the normal mode, you can grab a landing elevation. By default, it will use the destination from the FMS. Whoops, not that. And you can also have altitude select mode, which switches it to a specifically selected cabin altitude. So I have it set to 0. So as soon as I go into altitude select mode, you can see that the cabin altitude is now proceeding towards 0 feet. The sea level altitude here is about 700 feet or so. So it's very slowly going down. If I switch this back to normal, we're going to see it switch to landing elevation with no feet entered yet. And the outflow valve is going to open to return us to our sort of ambient pressure that we have here on the ground. And with this simulation, we've got the outflow and inflow valves simulated. All that stuff is working. And the schedule actually is the exact same schedule that the real plane uses. So all of the pressurization limits and what the targets are all exactly from the real manufacturer data. So we're using the same thing that they are. But let's check out a couple other interesting pieces about the automated modes. Here we are at the runway, configured for a takeoff. And let's watch the cabin altitude once we advance the throttles to the takeoff position. Well, that's interesting. It went down. Why did it do that? Well, what's happening here is in order to prep the plane for takeoff and increase passenger comfort, the plane pressurizes just a little bit under where the current ambient pressure is. And that makes it a little bit easier once the plane starts climbing to acclimate to the climb pressure and to make it so that people's ears don't pop quite as much. So it's a feature that actually is in a lot of modern pressurization systems. You see it in the Embraer jets, things like that. And it just makes passenger comfort a little bit better. So yeah, we can see it again. Push up, we get a little bit of pressurization, just a touch. It's like it doesn't really move the needle much. You don't actually see it even go down as far as feet goes because these are all like 50-foot increments. But it's about 10 or 15 feet or so, just enough to kind of seal everything up and make the passenger comfort a little bit more. And we simulate that. This one's a little harder to show, but we'll try and show it. Do a quick landing here. Going to be a little bit difficult. I'm kind of flying off to the side of the airplane so we can see this pop out. But what happens is that it will pressurize just under the landing field pressure so that it doesn't miss the target in case the conditions are not quite as expected on the ground. So we're just going to roll off here. Floating a bit, floating a bit, floating a bit. Let's get some weight on wheels. Okay, not too bad. I'll take it. And you notice as soon as we hit the ground, it's bringing us down to the pressure that we expected. So there's a little bit under and a little bit up and then a little bit back down. And that just makes it sure that it's all equalized and you're not missing your target in case, you know, barometric pressure is not what is expected when you get to the field, or it's extremely high or extremely low, something like that. So we simulate that little bump as well. In a different scenario, here we are at Telluride, which is quite high. You can see we're about 9,000 feet here. And you notice we've got a little informational cast message, which says cabin altitude. And what that is telling us is our cabin altitude is actually quite high. And with this message, it means that the altitude system, the pressurization controller, has gone into high altitude mode, which means that it's raised the cabin altitude limits a little bit, and also it will be descending once we get off the ground as opposed to ascending, which we can show. So here we are, we've just taken off from Telluride, and you can see that our cabin altitude is actually decreasing, and it's decreasing at a pretty good clip too. So the other thing that high altitude mode enables is the ability for the system to decrease the cabin altitude a little bit more rapidly than normal. Normally you'd go 500 feet per minute would be the rate. In high altitude mode, it allows it to go a little bit faster so you can get to your target a little bit quicker. So you can see we've got our delta P increasing. And we're going to cruise down here towards about 5950 feet. That's where the longitude sits. So that's the high altitude takeoff. You go down instead of up. Similarly, this also happens in the opposite direction. So now I'm landing at Telluride, descending towards Telluride. I've got it in active pause here just to make it a little bit more manageable. But as you can see, we've got our cabin altitude going up. And it comes from our 5950, and it will go up towards the landing elevation, which we have here of 9,037 feet. And how does it know when to do this? Well, a couple of different ways. The controller looks at the flight phase data, which comes from the FMS, or it also has a backup where it will use the time to go to the destination in order to compute whether it needs to start doing the ascend to the cabin altitude, or to the landing elevation, I should say. And this process is done, you know, whether or not you're in high altitude, but there is a lot going on there that the controller takes a look at to make sure that the, you know, pressure reaches the correct altitude for where you're landing. Circling back now to the bleed ear system, you might be asking, well, how do all these things interact? Well, let's set up a scenario here. So what we've got is we are in ACM only mode. Let's pretend that we had a heat exchange problem, but we decided to take off with just the ACM. Maybe we're taking the plane to maintenance. And en route, we now have a left engine failure. So as you can see here, as a result, ACM only mode requires that the left pressure source be pressurized. But that is not presently coming from the right side. So what the plane is telling us here with bleed isolate norm warning is you're in a situation where you actually need to use the bleed isolate crossflow, but it is still selected in norm. So it's telling you actually this is not the right mode for this issue, for this situation. And I sort of stopped us here so we can see what's happening. So we are at 6350 of cabin altitude, and this is higher than what we would normally want to be, which is 5950. So I've kind of paused it at this spot just so we can illustrate what's happening. We can no longer pressurize the airplane any further because we have no airflow into the ECS system. You need airflow into the ECS, and the ECS provides the pressurized air into the cabin. Currently, none of the outflow valves will open, so your cabin altitude will not necessarily climb, but you won't get any additional pressurization. So what we need to do is we need to rectify this issue. And the easiest way is to do what the CAS message says, is to change out of norm for your bleed isolate. So if we switch that over, now we've got flow from the right side engine. The right side engine is now powering the left bleed manifold, which goes to the ACM. The ECS has supply air, has pressurized air, and now you can see we are descending towards our 5950 feet. So all of this stuff is properly tied together. All the manifolds are simulated. All the parts are simulated. So all these things can have real effects, and you can practice those failures just by shutting a few things off. And lastly here, just a quick look at our environmental control system. We've got a hot day, 33 Celsius, quite steamy. And we've got our bleed airs off just to illustrate. With no airflow, we're not getting any cold air into the environmental system. So a couple things happen here. The supply air has temperature controllers that mix cooled air or heated air, potentially ram air if it's cool coming from the outside, using the heat exchanger and the air cycle machine, and will control these supply temperatures in order to make the cabin reach the target temperature. So target temperature here, we've got 21 Celsius, very comfortable. And if we then switch our bleeds back on and get some flow into our ECS system here, you'll see immediately we're going to start to see differences in these temperatures. So our supply temperature will start to come down probably a bit. It depends on how cold it wants to get it. It tries to use a temperature differential that's efficient. But you can see already that we've got our current temperature coming down a bit. So we've got some nice cold air coming into the cabin. And what we simulate here is we simulate the air mass of both of these separately. So we simulate the air mass of the supply air, we simulate the air mass of the cabin air, as well as the cockpit air. And the temperature controller is reacting to that thermal mass and is reacting to the trend of the temperature itself. So it doesn't want to bring the temperature down too fast. You don't want to blast people with cold air from the vents. That's too cold. But you do want it to come down at a reasonable speed. So the controller has sort of a slope here, and all of that logic is built in, and there's independent controllers for each supply line, for the cockpit supply line and for the cabin supply line. So we've got that simulated, as well as the recirc fan speed, which you can increase to high here pretty easily. There's a GTC option for it, or if you're in high flow mode, which opens up some extra valves and puts this whole thing into more of a high flow system, especially good in these hot days. You can get your recirculation fan up to high that pulls air from the cabin and recirculates it into the supply air, so you just get more airflow. And if you have this in the flow mode in high, then you get the recirc fan also will default to high. So right now it's just an auto, which defaults to low. But if you put flow in high, then you'll get high recirc fan also, as well as high flow through the rest of this stuff, which can allow you to cool your cabin a little bit more effectively and quickly. And I think that's about it for this area of the pressure system. And we'll move on now to the anti-ice. All right, we've got our anti-ice synoptic open here, taking a look at it, and here's our ice protection control center. Pedostatic, wing, stabilizer, individual engine, anti-ice. The system in the Longitude is relatively straightforward, but also has some automation to it. So you can see here already, we just loaded on the ground. We're sort of starting on the runway to make things easy. And you notice that we've got the temperature increasing on the windshield panels. Now, windshield heat is automatic, fully automatic, and will come on with certain buses. So if you have some buses removed, you won't necessarily get all of the panels. However, in normal operations, you do get all the panels, and there are temperature controllers that will adjust the current going into each heating panel, and we'll try and maintain a consistent, nice toasty temperature for the windshield panels, so you don't get any ice in there or any freezing, precipitation that might stick. Next here we have our individual engine anti-ice, left and right. And turning those on will engage the anti-ice for that engine, which heats the leading edge. You see this little leading edge indicator. It's kind of silver. That's silver on the actual plane, and will prevent any ice buildup on the leading edge of the turbine inlet here, so you don't get any ice chunks falling into your fan, causing turbine damage, etc. So that's anti-ice for the engines, and it operates the same for both sides. And you could just switch those on or off here. It's not automatic, it's fully manual, and that's all the pilot really has to do in order to engage engine anti-ice. Next, we've got wing anti-ice here, but I'm going to leave that one for last and just go through these other two first. Stabilizer anti-ice is actually a mechanical system. There's basically little hammers inside the leading edge of the stabilizer that slightly deform the leading edge of the stabilizer and break chunks of ice or any ice buildup from the stabilizer itself. We can't hear that from here, but it's kind of a knock, knock, knock sound. And that will remove the ice from the stabilizer. And again, that is also just pilot selectable. It's either on or it's off. Pitot heat here is also a nice little automated pilot workload gem, as in the norm mode, you actually don't have to do anything with it. As soon as you leave the ground, the pitot heat will be engaged because you have sufficient airflow and you won't be burning it out. And when you land, pitot heat will be turned off. However, if you want to force the pitot heat to be on, you can switch it from norm to on, and you will get an indicator telling you that the pitot heat is set to the on mode. Just in case for some reason the pitot controller is not doing exactly what you expect, or you get some weird readings, weird speed readings or something, and you're going, hey, we're in norm here, we should have pitot heat, but just in case, I'm going to switch it to on and make sure that we for sure have pitot heat. But we do simulate the pitot normal mode controller, so you will get pitot heat as soon as you leave the ground, and it will be turned off as soon as you land. And finally, we have wing anti-ice, the most complex of all of the anti-ice systems, and that draws from bleed air. And there's quite a few things happening here that we will illustrate. So when I turn wing anti-ice on, we're going to note a few things. First, we see the engine actually spool up. Then wing anti-ice comes on and the engine spools back down. Why is that happening? Well, what happens is, in anticipation of the additional bleed air load, the engine actually spools up to drive the compressor a bit higher, because it requires a bit more airflow in the high-speed compressor in order to power this bleed air demand, which is quite high for the wings. And once that bleed air hits, once the air is coming out of the compressor stage, then you'll notice that the N1 does drop because there's not as much air to drive the N1. So the engine is anticipating this drop and trying to even out that for you, so you have relatively the same fan speed before and after. We are simulating both the controller side of that, which is pushing the engine speed up, and we're simulating the N1 drop side of that with some custom turbine logic that says, okay, we're getting this much bleed demand, and therefore the N1 is going to come down a bit. Something you'll also note here is we've got a bunch of temperatures displayed. So we've got down here our bleed air supply temperature, quite high. As it travels down the lines, it loses a little bit of heat in the process. These lines obviously need to be heated as well. So there's a delay between these all reaching the same temperature. And then we've got the actual leading edge lines, which have a number of tubes in them that sort of spit this hot air out at the leading edge itself. And so we have sensors on the leading edge that are giving you different temperature readings. And you notice that these are slowly increasing. And all of this simulation is based on the outside air temperature. It's based on how much airflow is running over the wing. It's based on what mode you might be in for bleed air, high flow mode. We'll make this go a little bit faster. And if we turn wing anti-ice off, we'll see the N1 pops up a little bit because the bleed air demand just went down, and then the controller resumes the normal mode, so it doesn't do the extra acceleration. So then we see that come back, N1 come back down again. And you notice here that these temperatures are not going down very quickly. Why is that? Well, that's because we are still on the ground. We're not moving through the air. If we were moving through the air, we would see these temperatures going down much more quickly because there's more airflow crossing over or passing over the leading edge, which cools these bleed air tubes. And that will sort of proceed backwards because this is the only part that's exposed to air. So these will cool first, and then sort of the interior here, and lastly, the bleed air supply lines, which are tucked way back and don't cool particularly fast. So we have a very complex temperature simulation here that governs all of these different pieces of the wing anti-ice system. And that basically rounds out the ice protection system for the Longitude. And now let's take a look at the Longitude's fuel system, which also has a lot of fun automation, some behaviors we can take a look at, and a lot of cool simulation stuff going here. So I've got the fuel system synoptic open, and we'll just go through some of these things pretty quickly from top to bottom, and then we'll go into each of the individual systems and controls sort of in order. All right, so starting at the top here, we've got our total fuel. And that is in pounds. A question we very often get is this possible to change to kilograms if I change some setting, either for the EIS or for any of the synoptics? And the answer to that question, strangely, is no, it's not possible to change that. The plane was only certified in pounds, therefore Textron does not give you an option to change the EIS or the synoptics to kilograms. So even planes that get delivered into Europe or other areas where kilogram measurements are much more common, these displays will always be in pounds. So that's one thing that's interesting to note there. All right, moving on here, we've got our fuel quantity. Left quantity, right quantity, indicated by this bar graph. This little area down here is the fuel warning area. These numbers will turn yellow and we'll start to get some CAS warnings once we move into that area. We also have the fuel quantity in pounds. We've got the temperature right here. So that's all for fuel quantity. And then moving over to the right, we've got our gravity cross flow valves. Those are passive valves that allow the fuel to be balanced between the two tanks just by gravitational action. So just by the fuel flowing from one side to the other. And those will open when the gravity cross flow is open. Moving to the left a little bit here, we've got our recirculation pumps. Those recirculate the fuel within the wing in order to keep the temperatures constant, not get any hot spots, make sure that there's no dead pickup areas, and just keep the fuel kind of recirculated. That's why they're called recirculation pumps. We've got the lines also indicated here. Moving down and a little bit, we've got the fuel boost pumps. Those are electric pumps, which increase pressure into the fuel lines when necessary. Right here, we've got actually the pump itself is not indicated, but there are scavenge ejector pumps used when the fuel quantity is low in order to get greater pickup from the fuel area, as well as when the fuel is cold. So this fuel actually comes from sort of a hopper tank, which is a little bit isolated from the rest of the wing tank. and that provides some thermal isolation from the hot fuel that returns from the engine from the rest of the fuel. So there isn't just superheated fuel going throughout the entire fuel mass. So there's a hopper tank here, and when the quantity is particularly low, you need some extra oomph to pull some more fuel out of the hopper area. So these scavenge tanks will activate, and these are actually the valves for the scavenge ejectors will activate, and here's the valves for those. Now right here we have indicated the primary ejector pumps, and those use motive flow from the engine. So what that means is high pressure fuel will come into sort of this nozzle here, and then by Venturi effect, the greater amount of fuel will be sort of sucked up through here and then pushed out through the main throat of the ejector. And that will provide the fuel to the engine. So there's sort of a two-way system here. Fuel goes to the engine, fuel also returns from the engine to sort of power this whole thing. And then there's there's an engine-driven pump inside the engine itself that keeps this whole thing running. Down here, we've got our main fuel valves for each engine on the left and the right. And then we also have our APU valve, main valve, fuel valve right here. And then finally, we've got our fuel transfer valve, which during active fuel transfer is opened in order to push fuel from the right to the left or from the left to the right. An interesting bit about these gravity cross-flow valves is they're actually not available on the ground. If you as a pilot press this button, the gravity cross-flow controls, it remains closed, nothing happens. The reason for that is because it would be bad, for example, if you accidentally left the gravity cross-flow open in a position where the aircraft was parked unfavorably. So say tilting to the right or tilting to the left, you could end up with a very large fuel imbalance that would take a long time to transfer from one side or the other. So the automation prevents you from accidentally doing that and will automatically close the gravity cross-flow valve on the ground no matter what the pilot has it set to. So just a nice bit of protection there. And speaking of the pilot selectable controls, we have the fuel boost pumps here. Norm is in automated mode. You can also select those to on. You have the fuel transfer switch. Left sends fuel to the left tank from the right tank. Right sends fuel to the right tank from the left tank. And finally, you've got the fuel recirc pump. That's norm or off. Norm is in automated mode. Off is switching the recirculation pumps off. And we'll go into the behavior of each of the norm modes as we go through each of the systems. But first, we're just going to start the APU, and we'll see exactly what the automation does when you get the APU started. Okay, so let's just start the APU here. And we'll just switch it straight over to start. And you notice immediately that the right fuel boost pump comes on. If we were looking at the PFD, we'd also see a CAS message for that. And the reason that that comes on is because firstly, we need to get some fuel into the APU, obviously. That's the first bit. It's starting, so it needs to get going. But the other piece of this is that the APU itself does not have enough return pressure for motive flow from the primary ejector pumps. So what has to happen is a fuel boost pump is required in order to pull fuel from the tanks and push it to the APU. It can't actually maintain this ejector pump cycle on its own. So that's why this pump lights up when you first start the APU. All right, let's get the right engine started here. Switch that to run, hit the start button. Now, if the APU was not already running, this boost pump would come alive as soon as we signaled that we wanted to start the engine. And that is for a couple reasons. One, the engine-driven pump is not yet producing enough fuel pressure through motive flow in order to provide fuel to the engine. So we need the boost pump in order to get that fuel line pressurized. Now, you'll notice here that this ejector pump became green, which indicates that we no longer need the boost pump in order to provide pressure to the line. So even in the presence of the APU running, the motive flow in the ejector pump from the right engine is sufficient to pressurize the line actually for both. So we will see here that it's just this that we need. Now you'll also notice that the recirculation pump is on. In all normal operating conditions, the recirculation pump will be on if the engine is on, and that's again just to maintain the temperature of the fuel throughout the wing and make sure that everything is circulating the way that you want it to. Now you can turn this off manually in case of some kind of checklist or flow or emergency that dictates that you should, but in all normal circumstances, this will be on. Now you'll also notice here that we got an increase in our fuel temperatures. Now this temperature is just the temperature at the line. And so this represents sort of an area that's very close to the engine in the fuel line. You'll notice that this is fairly warm. However, the temperature in the tank is not rising very quickly. Well, again, that's because we simulate the fuel mass. We also simulate as the mass of the fuel decreases as fuel is burned, the thermal sink, basically the amount of heat that you can sink into the fuel also decreases. And so with very low fuel quantities, this temperature will affect this main tank temperature a lot quicker. Likewise, when this has a lot of fuel in it, this temperature here will not affect this very greatly. So again, we're sort of simulating all that. But now let us start up the left engine. So we're going to indicate start. And we see our boost pump come on, exactly what we want. And we'll get this engine started. All right. And now we've got ejector pump, motive flow. And as soon as we settle, this boost pump will come off. There we go, boost pump off, recirculation pump on. And now we've completed the start process. So we're just going to go through here a couple more interesting tidbits about the fuel system. First off, let's go up here to our weight and balance panel. And we're just going to decrease our fuel quantity until it's particularly low. Keep going, keep going. Okay. Now, if you see here, we've got a green line coming into our main line, and that's coming from over here. Well, again, this is our scavenger pump, and this is showing us that the fuel is low enough that we need to engage the scavenger pump in order to get sufficient flow into these lines. And that also automatically opens up the scavenger pump valve. So that's our scavenger pump system. As well, if we go back up, scavenger pump turns off, and we'll just close that. Another interesting thing is we can manually adjust the boost pumps with these two switches. So if we turn the right one on, we'll see the boost pump come on. And that actually also turns the recirculation pump off in order to maintain the right amount of flow. And since this is already pulling fuel from the scavenger area, this kind of maintains that the flow is already sort of pushed throughout the wing regardless. So the recirculation pump is not necessary when the boost pump is on. And likewise, you can do this on the other side, turn the boost pump on. Again, scavenger sort of comes into play here. You'll see the line, but that's really just the pickup for the boost pump itself. It looks like it's coming from the scavenger area, but the scavenger valve is not open, so it's a little bit misleading. But it's just sort of indicating that, hey, it's coming from sort of the hopper area. Now here's sort of an interesting weird thing. The fuel transfer system also uses the boost pumps. So let's say I want to go from right to left. So I switch this on. Now we've got the fuel transfer valve open, and we've got the fuel boost pump running, which pushes fuel through the transfer valve into the other tank. Well, what's interesting here is you can actually configure a situation in which these push against each other and there is no fuel transfer. So for example, if I turn the left boost pump on, now you notice this is all green. Well, that means that because the transfer valve is open, fuel is pushing into the transfer valve from the left side and from the right side. So there is no fuel transfer even though you have this selected to the left tank. And if I look up here, we should have a CAS message telling us that there's an issue. Correct. Fuel transfer failed. This is saying, hey, you've configured this into a situation that is actually not facilitating the fuel transfer that you were looking for. So You definitely want to resolve that, and we can obviously resolve that by unconfiguring it from our very weird setup here. And now we're back to the normal transfer. So just a couple interesting quirks about the fuel system. So just some final notes on the temperature simulation of the fuel here. In addition to the scavenge pumps sort of waking up when the fuel temperature is low in order to get more heat from the fuel line back into the rest of the fuel mass, there's some other stuff that goes on here. So these fuel line temperatures will change much more rapidly with air temperature as they just go kind of through, are routed straight through the main nacelle spar. So they're not super isolated from airflow or from temperature changes. So these will change more rapidly. But as mentioned, the main tank temperature will change very slow. But the other thing to note here is this is all based on airflow that goes over the wing itself. So it's based not on just the outside temperature, but it's based on the ram air temperature. So the compressive heating and friction of the air as you are going at speed in cruise changes what the fuel mass will be exposed to. So that's all sort of relevant to this particular number here. So that's why ram air temperature is particularly important, because it tells you exactly what temperature the skin of the aircraft is experiencing, as opposed to just what temperature is it in the air. And this fuel stuff is all reacting to that kind of temperature because that's exactly what is diffusing from the wing surface into the fuel itself. So it's all very well and thoroughly simulated, and it's just a really cool system that the Longitude has here. All right, now we're going to talk a little bit about flight controls here. And the flight controls on the Longitude are relatively standard, but there's a few kind of cool quirks that we'll go into, mainly around the spoilers. And we're going to talk a little bit about the brake simulation as well, but just kind of going through the flight controls here. So you can see here we've got ailerons and roll spoilers. So the ailerons, and I'll get my mouse over here. Oop. There we go. All right, ailerons are these guys. Roll spoiler panels are those guys. And you can kind of see them going up and down as we move the controls. And then we've got our elevator, which you can see moving up and down over there. Pretty standard. As I mentioned before, the ailerons, they are mechanical linkage. The roll spoilers are hydraulic, and we already kind of talked about what happens when you lose the hydraulics. And then we've got flaps here. I've got them down flaps 1, so they're down just 1 notch. Each little line here indicates one of the notches. And then spoilers, if I go down and actuate the spoilers, you can see those spoiler panels come up. They're not full because they're not the full ground spoiler panels, but just they just come up a little bit. So some people ask, what is the ground spoiler situation in the Longitude? Do I have to do this when I hit the ground? How do I arm the ground spoilers? Well, the ground spoilers in the Longitude are completely automated, so the pilot doesn't really have to do anything in order to get them to work. They just automatically become armed after 35 knots. And we're going to do a quick little test here, and we'll show exactly how that works. Okay, so let's just get rolling here. I'll take the parking brake off. And we'll just go full takeoff thrust. We're not really going to bother with anything else, any setup. And there we got airspeed is alive, so we're above 35 knots. So if I reduce the thrust back to idle, you'll notice we've got full ground spoilers come up. So they are 100% automatic. And let's just do some braking here. And we can easily repeat the cycle. So if we get under 35 knots, the arming cycle gets reset. So we have to get above 35 knots again in order to get the ground spoilers rearmed. And that should be relatively quick. Airspeed is alive. Idle power. Ground spoilers come out. Now, you might be asking what happens if we need to execute a go-around. Or let's say, you know, we've got weight on wheels and we touch down a little bit. We need to get back into the air. So we can actually show what happens in that situation here. So we're going to do takeoff thrust again. Get us above 35 knots. All right, airspeed is alive. Idle power. Ground spoilers out, and takeoff power, they immediately retract. So that's sort of the automation there that allows you to execute a go-around in that circumstance. And now, as you'll see, we've got some brake temperature action going, and there's, you'll see, you probably would have seen already, we've got some brake pressure changes. So I'm going to start us over back at the other side of the runway, or the beginning of this runway rather, and we'll go over what the brake simulation is doing. Okay, so on the brakes, we have a fairly complete simulation here as well. We've got a full temperature simulation that simulates the heat going from the brake pads to the calipers, and as well as then into the rotors. And the rotors have a certain thermal conductivity and thermal mass, just like all the other temperature simulations that we've been talking about. There's quite a few on this plane because there's a lot of places where you can see temperature. So it's a very important data point, and we absolutely want to get that right. So we've got a whole temperature simulation for the brakes, and we also have a pressure simulation and actuation simulation. So in the Longitude, these are automated anti-skid brakes, so they will modulate the pressure in order to prevent you from locking up the tires. So you're not able to actually flat spot these tires by locking them up just by applying too much brake pressure. They're anti-skid. So we're just going to do a first quick test here for the temperature simulation. We're going to do something that you don't want to see in real life, which is, let's pretend that we had a brake lock failure and the brakes locked while we are on our takeoff roll and we didn't notice immediately. So we're going to actually run with the brakes in the locked condition for a little bit of time and then pull the power back. So let's do that right now. Just going to adjust the view a little bit here, and we'll get our takeoff roll going. Brakes off. Takeoff power set. And we've got airspeed. And we're getting close to VR. And let's put the brakes on. Why are we slowing down? Why are we slowing down? This is not good. What's going on? 3,000 PSI. Oh wow, look at our temperatures are going up rapidly. Okay, let's bail out of this takeoff. Ground spoilers come up. And let's see what's going on with the temperatures now. So you can see that they rose really quickly. Each brake has a slightly different thermal mass. They're not just all copy and pasted, so they are all a little bit independent and act differently. But you can see the temperatures now are going down relatively slowly. And that's because we're not moving. We've got the brakes on. So with the brakes on, the heat is still sort of soaking into the rotors and diffusing through the calipers. So these temperatures are not dropping very quickly. However, if we take these parking brakes off and we start moving a bit, we'll get some airflow to these brakes, and we should start seeing these temperatures go down a little bit more quickly. Yeah, I can see here at taxi speeds, we're already seeing the brakes cool off much faster than if we were just parked. So we do take the ground speed, the wheel speed, RPM into account when determining exactly how quickly the wheels are being cooled, how quickly the brakes are diffusing heat into the air. So all that stuff is simulated. So the brakes are pretty cool. I'm going to set us back to the beginning of the runway again real quick. And we're just going to take a look now at the brake pressures, at the anti-skid function. All right, we're back at the start of the runway, and we're going to do a similar test. We're going to take it off to about rotation speed, take it up to rotation speed, and then we're going to apply the brakes. And I just want you all to watch the pressures here as that happens. We're going to talk a little bit about that. So brakes off, take off power. And we're rolling. Airspeed is alive. All right, getting close to rotation speed here. And I'm just going to cut it and hit the brakes. And you notice that we see 400 PSI here. And now as we slow, this is going to increase a bit and then jump. Yep, now we're at 3,000 PSI. So what happened there is the system detected the brakes, or the wheels, are rolling quickly, and we don't want to over apply pressure in order to avoid skidding the brakes and skidding the tires, or locking the brakes and skidding the tires. So the anti-skid system will actually modulate the brake pressure in order to prevent skid. So the maximum you'll see on a roll, once you're fully rolling, if you're sort of at those at landing speeds or at takeoff reject speeds, is about 400 psi. You will see some spikes to 700 or 800 psi when you first land, and the system is sort of acclimating to your new wheel speed, and the wheels are sort of spinning up. But it's all in service of maintaining a lack of tire skid. So you do get that initial burst of stopping power, and then it's going to detect, okay, I'm sort of at the threshold of skidding these tires. I'm going to pull it back down. And then when you're fully stopped, there's no concern there for skidding the tires anymore. So you can get the full 3,000 PSI brake pressure. So again, all that stuff is simulated. And we do look at the wheel speeds and all that kind of stuff to determine exactly what brake pressures we can apply and to avoid tire skid. So that's the brakes. All right, now we're going to check out the pre-flight synoptic. And there's a lot of cool stuff here also. I know I've been saying that a lot, but some interesting things. All right, so oxygen pressure here at the top. We don't really simulate an oxygen system. The sim doesn't really let you, simulate an oxygen out situation, so we decided not to really focus on that. But a lot of other stuff here. This propulsion section we're going to get to a little bit later, so I'm going to skip that for now. And then we have a number of tests listed here. So auto test, power on test, taxi tests. The auto tests come on when specific conditions have been met. So in the case of fuel pressure, it's when the lines have at least started to be pressurized both. And then the system will check and make sure that it's holding the pressure, and it'll get a pass there. And then hydraulic pressure A and B, as long as those have pressure, once those are pressurized, those will also go from pending to pass, and pass as long as they continue to have pressure, there's no leaks. And as you remember from the hydraulics section when we were talking about that, with the parking brake on, the PTCU is automatically pressurizing those lines as soon as you start the plane. So that's why these are already in a pass condition. You won't normally see these go from pending to pass once you power up the airplane because it's relatively quick. However, if you happen to have the hydraulics in shut off and you had the PTCU off, these would not go immediately to pass until you got some pressure in those lines from the PTCU. And then here we've got other power on tests. These happen as soon as you power on the airplane. Bleed leak, just checking to see if there's any leaks in the bleed air system that got thrown by any detectors. Cockpit voice recorder, flap system, if that's working. Fuel level low. If you've got low fuel when you power on, this will not be a pass. The Longitude has an ice detection system, which we also simulate. And if the ice gets to a certain level, it will actually give you a little ice indicator down in the EIS here, which is really neat. So that's checking that system. And then pressurization, that's the ECS and pressurization system. It checks some parts of that. Normally this stuff will all just be pass. And then here we have our taxi taxi tests. And these will happen as soon as you start taxiing, and we'll show those happening in a bit here. But the first thing we're going to show is these fuel pressure tests, and we're just going to get these engines rolling. And we're going to start the second engine, or the right engine first here. And we got ignition. I feel like this video would have been about, I don't know, 30 minutes shorter if we didn't have to start the engines so often in so many of these demonstrations. All right, so we've got light off there and we're settled. We'll just start this other one, and as soon as we get it kicking, you're going to get a pending, and it's waiting. And now we've got some fuel pressure being introduced by the boost pumps. And as a result, it checked the lines, and the lines are now pass. So that's it really for those. And one thing about the power on test is not only do they come on or do the test when you power the airplane on, but they also check all this stuff when you shut the airplane down. So if we actually shut the engines down here, we should see these tests cycle again. There we go. And we get a pass again. So those are the power on tests. All right, now onto the taxi checks. You see we got spoilers, tail de-ice, wing anti-ice, probe case heaters. These are all active tests that run as soon as you get to about, 5 knots or so of ground speed taxiing. And the spoilers check will actually run the spoilers up. The tail de-ice check, it runs some electrical checks on the tail pneumatic de-ice system. The wing anti-ice will actually run an entire cycle, turn anti-ice on and off and make sure that everything actuates and is pressurized. And as long as you get pressure and everything in there, you'll get a pass. And then checking the probe heaters and case heaters. So I'm just going to demonstrate that, and I'm trying to have everything up here as much as I can. You should see the spoiler panels go up and down. With the tests, you should see this stuff actuate with the wing anti-ice test. And so we'll just get a little ground speed going here. So I'll take the brakes off. Make sure we get enough speed. It's hard to see. Hopefully I'm not running into anything. You see some stuff went to testing and pending. We got a full cycle, and we passed. And so those automatically activate once you start taxiing. And those will get reset once you shut the plane down. So you don't have to really worry about that stuff actuating every time you taxi. It's only going to do it that one time. And then next we'll get into this no takeoff area right here. The no takeoff window here is sort of a quick checklist to make sure that you have everything that satisfies your takeoff conditions. And if you don't have anything, or if you have things here that you need to check still that are in the wrong position, you will get this no takeoff message in white. And if you attempt to take off, you'll get it in red. Now, when you attempt to take off, these current statuses will sort of load into this active on previous, so you can see exactly what was incorrect the previous time that you got a no takeoff. So if I advance here to takeoff speeds, if I just push the throttle all the way forward to the takeoff position, we get the red, we get the blinking, and you see active on previous gets loaded for these two, stabilizer trim because we don't have it set properly, and flaps because we don't have those set properly. So we can remedy that. We can set the flaps. We'll set the flaps to 1. And we will roll the stabilizer trim down to about -6 or so. Sorry, not -6, -4.5. And now we have everything okay. So if I push this again to takeoff position, to the throttle takeoff position, now we see everything was okay. That message goes away. Active on previous. None of them were active previously in the takeoff. Let me just pull that back down. So these little asterisks go away. So now we've got everything passing now for the takeoff state, and we can proceed to take off. And so that's pretty much it for the pre-flight synoptic. It's a nice little overview of what's happening in the plane just to make sure that you're ready to go. Every Longitude pilot will always check this. This is one of the panes that they have up during their pre-flight operations. So it's a very popular one. You know, the things, this is really nice right here. This no takeoff section is really nice because a lot of times you get the message, we get questions from users as to why it's not working, and the Longitude is just trying to help you out, and so it gives you all the things that it's checking for its own no takeoff cast warning, and so as long as you've got these satisfied, you're ready to go. So one thing that people don't really realize is just how in-depth the GPS simulation is in this aircraft. And furthermore, really in all the avionics that we produce now, this models each individual satellite position, which you can see here, using actual orbital ephemeris data straight from NASA and using real orbital mechanics equations to derive the positions of the satellites from that orbital ephemeris data. So the positions that you see here are actually real positions of these satellites at this place in time from the ephemeris data. And so what we have here is a constellation diagram, and it's sort of a sky map This point represents here directly straight up from your aircraft. This is 45 degrees forward from the aircraft, and this is 90 degrees forward from the aircraft. So this would be like the horizon. So this outer line here is the horizon. So there's some satellites that are pretty close to the horizon. There's a couple that are closer to being above us directly. And our angle to those and our relative distance as a result of that angle sort of plays into exactly what the signal strength is of each individual satellite. So satellites that are closer to the horizon that we don't necessarily have a good angle at or are obscured will get a much lower signal. And you'll see it here as these bars. And you'll also notice that we've got all the numbers. Now, these are the actual identification numbers of the real satellites. These ones starting with the ones are actually the SBAS satellites. And you'll see here we're also calculating some figures of merit, horizontal figure of merit, the vertical figure of merit. We've got our position calculated from all that, which we get from the sim. And then we've got our GPS altitude, our current ground speed, track, all that kind of stuff. And you see we've got actually 2 GPS receivers simulated right now. They're both slaved. We've got the pilot and co-pilot slaved to GPS 1. And this 3D diff nav, what does that mean? Well, that means that we've got a differential solution. It's not just like a few satellite solution. We're actually generating more precise vertical data as a result of getting this differential solution. And the differential comes from these SBAS satellites. The SBAS satellites transmit to us some time code corrections to get us more accurate data, and those time code corrections are sort of forwarded to the satellites based on some ground stations. So this whole thing works together. Now, not every area has SBAS. The US has it, India has it, Europe has it, but if you're outside of the SBAS service area, this will not be active. And so we actually have that baked into the GPS simulation, the service area. And so you get SBAS either active or inactive, depending on where you are actually in the world, which is really cool. Now we can see what happens to the positions of the satellites as we change our time here. So if I just go and forward this a bunch, after a few seconds, this constellation will update, because the positions of the satellites have changed. Now, there are some that we already had, so they're already indicated here, and some that it might take us a while to find. So this is not normally the number of satellites that you would run with. So you see our horizontal figure of merit has gone up to 80 feet. Our vertical figure of merit has gone up to 49 feet because we don't have quite the number of satellites that we had before. But we can forward this even further. And you can see now we're acquiring some satellites. Sometimes it takes a little bit to get them because the receiver doesn't always know exactly where they're going to be in the sky. And it takes a while for all the signals to propagate down to the Earth and for the entire cycle of signals to be captured by the GPS receiver. So you see now we figured out where they are, and pretty soon we'll start actually getting solutions from those and tracking those. So once they light up green, we're getting a solution from that, and you'll see they'll start to all light up here pretty quickly. Yep, we've got Sat 1 there, Sat 25, yep. And some of these popped out of the differential solution because they're not all needed. So if you have a certain number of satellites, they're not all required for the differential solution. So it just depends on what situation you're in. If you're going to get differential data from every satellite, and some of it will be used and some of it won't be. So there's a lot going on there. I know that's a lot of information, but just wanted to go over that because it's a thing that most people never see, and you're never on this page and you just sort of assume that the GPS just sort of works. But there's a ton going on behind the scenes here with the GPS simulation. It's very, very cool stuff. And finally, last but definitely not least, we're just going to talk a little bit about the engine simulation here. So we've got the engines on. Just talk a little bit about our targets. So The engines here, we have a couple of custom things. As mentioned before, we've got custom turbine simulation to simulate bleed load, N1 loss of efficiency, stuff like that from the bleed air system. That's all custom. And some other stuff we have here is this FADEC on top is entirely custom. So the FADEC data, all the N1 targets, everything that you see when you're in all the different FADEC modes, which appear here right now, we're in the takeoff FADEC mode. All of these targets are sourced directly from the manufacturer data. We worked directly with the manufacturer in order to get this information loaded into this plane. And these targets are not something that we guessed at. So they're something that exactly matches the real aircraft. All of the correct targets at all the different altitudes, as well as all the correct target types. We got takeoff targets, we've got climb targets, cruise targets, all that kind of stuff, as well as auto power reserve targets, manual power reserve targets. All those things are 100% correct, accurate, faithful to the real deal, and direct from the manufacturer information. That FADEC is super complicated. There's not a lot that you can see because, you know, when you do it, the engine just goes where you think it should go, right? This seems very basic. But all of this is behind the scenes dictating exactly what the minimum and maximum of your throttle position are, exactly what they're going to be when you go into the various detents, all that kind of stuff. It's all simulated. The other really interesting thing here is the autothrottle, and we'll just go through a couple things about that real quick. So we've engaged the auto throttle system, which is this button at the back of the throttle. It's a little bit hard to hit, but even in this default cockpit view, if you just kind of get over this sliver, you can hit the button. And we've hit toga to engage the takeoff reference mode. So that will engage the takeoff pitch reference and roll hold reference, which you see here in the mode enunciator. And you see TO here for the auto throttle itself. And that is the takeoff mode for the auto throttle. We get some questions here, and I'll go through this. So in older versions of the Longitude, when you hit the takeoff, when you hit toga and you were in auto throttle, the throttle automatically moved for you, but that is not the case anymore in the new Longitude block software. Actually, it goes into what is called hold mode. And you'll see here, if I advance the throttles, it actually goes to hold. What does hold mean? Now we get a hold fail because I kind of pulled that back too fast. But what hold means is, hey, I've completely disengaged the auto throttle servos from the throttle levers themselves. And the reason for that is because the last thing you want is on the takeoff roll for the auto throttle to be moving your throttles for you by accident. So even if there was a failure in the auto throttle system and it computed something funky and it started running those auto throttle servos, they're not connected to the throttle lever anymore. So you have full control as a pilot, and you don't have to try and override the servos like you would be if you had a failure in some other aircraft and the auto throttle was working against you. Now we've got all the real Longitude auto throttle modes simulated as well. We're not going to go through all those here because this is more of a mechanical systems video, but one last engine piece that I want to go through is the power reserve. Now I'm sure nobody has actually hit these buttons and they weren't even available in previous versions of the Longitude, but these buttons actually do have a function, and we'll just go into exactly what they do. So you've got two buttons here. There's a button labeled manual and a button labeled auto. And if I hit manual, it goes to on. And what that means is when I advance the throttles, I will get my manual power reserve. And that's a little bit of extra power that you would normally only get if an engine went out. So if an engine goes out, the engines are authorized to deliver you just a little bit of extra kick, not for very long. You can't keep it on more than a few minutes, but you can have it on. So it's supposed to, get you off the ground. You got that little bit of extra kick. You've got a little bit more climb speed and climb rate, which is exactly what you want in an engine out situation. And that happens automatically when you lose an engine. However, you can turn it on manually just by hitting this button. And if I advance the throttles here, you see this changes to APR, and that's for the power reserve, and it's a different target than the takeoff target. So if I turn this back off and I advance the throttles again, you see we just go to takeoff. We don't get our power reserve. So we don't get that extra oomph. Now you can turn it on manual if you want that extra oomph in some sort of training situation, or if you're in some sort of failure that requires that to be turned on. However, if you're practicing engine out situations, you don't necessarily want to burn the power reserve because it's pretty hard on the engines to give that extra bit of juice. So what you can do is you can actually turn auto power reserve to off. So that means if I lost an engine while hurtling along the runway, I won't get that extra, that extra speed. I won't get that extra oomph. So that's helpful in training situations when you're not really wanting that. You don't want to use that, kind of burn that engine out faster than you really would need to. Because you're in a training situation, you're in a safe area, you're going to have enough climb rate to get wherever you need to go, and you just need that to be off. So you can turn that off. Now, auto power reserve will go on if you lose an engine, and I can actually turn an engine off here. I'll turn off this left engine, and we will advance to takeoff. And right now, auto is off. If I switch it back on, we get power reserve because we only have the one engine. If I switch it back to off, power reserve goes off. So that's what the power reserve does. It's a pretty cool little setup. Normally you wouldn't have to mess with this, but it is available and it is something that we simulate. So there you have it. That's most of the aircraft systems on the Longitude. Skipped a couple small things like the automated lighting system. There's some cool stuff there which you can read in the operator's guide, which is available on the Flight Simulator website. If you go to media and go to aircraft manuals, it's in there. It's about 130 pages. A lot of it goes over what we went over, but there's some other cool stuff in there if you're interested, including checklists and things of that nature. But you'll notice we just went into the systems part. We didn't even touch the avionics part yet. So you can see that there's a lot going in this aircraft, a lot going on in this aircraft. So is the Longitude deep? Well, I think so, but I'll let you all decide for yourselves. Until next time, I'm Matt. We'll see you guys. Fly safe.